So today we are going to talk about the topic which is STM32 ADC interfacing with HAL code example. So in this session I will explain the basic principles of ADC, also known as analog to digital converter, and closer look at the ADC hardware of the STM32 microcontroller. So to get you started, I will show you how to interface LM35 sensor, which is nothing but a temperature sensor, which is totally based on this ADC with the STM32 Nucleo F446RE and development board, and will display the output in PuTTY software. Okay, so the STM32 microcontroller is a 32-bit ARM Cortex MX based microprocessor that's commonly used in embedded system application. You already know that, right? So the STM32 has a built-in ADC peripheral that allows it to interface with analog signal. So the ADC module in STM32 microcontroller can convert analog signals into digital signals with varying resolution, like from 12 bits to 16 bits, which is totally depending on the microcontroller and its features. Okay, so the resolution determines the number of discrete values that the ADC can generate, which affects the accuracy of the conversion. Now let's talk about what is an ADC. See, an ADC is a device or module that converts analog signal into digital signal. So analog signals are continuous signal that vary in amplitude over time. On the other hand, digital signals are discrete signal that can only take on a limited number of values like zeros and ones. So ADCs are used to convert signals from analog world into digital signal that can be processed by digital circuits, right? Now, how do ADC work? See, ADC works by sampling the input analog signal at regular interval and quantizing the signal into a series of digital values. So the process of quantization involves mapping the continuous analog signal to a finite number of digital values. Okay, so the number of digital values that can be represented is determined by the number of bits in the ADC. So the process of converting an analog signal to a digital signal involves three steps. What it is? Sampling, quantization and encoding. Okay, and there is also another thing which is called application of ADC. So ADCs are used in varieties of applications including data acquisition, audio recording and processing, video processing, medical imaging, instrumentation and control system, communication system, something like that. So in each of these applications, ADCs play a critical role in converting analog signal into digital signal that can be processed by digital circuit. Now let's see the factors to consider when choosing an ADC. Okay, so when choosing an ADC for a specific application, there are several factors that need to be considered, including resolution. So ADC resolution refers to the number of digital bit which is used to represent the analog input signal. So in other words, you can tell it is the number of discrete level or step that an ADC can represent in the conversion process. So the higher the resolution, the more accurately the ADC can represent the input signal. For example, an 8-bit ADC can represent the input signal using 256 discrete value. So while a 16-bit ADC can represent the input signal using like some discrete values up to like 65,536 something, right? A high resolution ADC can provide more accurate measurements and is often necessary for applications that require high precision. So however, high resolution ADCs also typically have slower conversion rates and higher power consumption. So the choice of ADC resolution depends on the specific requirement of the application. And then the second thing is sampling rate. So sampling rate refers to the number of samples per unit of time that an ADC take of an analog input signal. So it is typically measured in samples per period or hertz. So the sampling rate is important because it determines the highest frequency component of the input signal that can be accurately represented by the digital signal. Okay, and then input voltage range. So the input voltage range refers to the range of voltages that an electronic device or circuit can handle as an input signal without causing damage or like malfunctions. For example, an ADC may have an input voltage range of like 0 to 5 volt, which means it can accurately convert analog signal within the range to a digital signal. If the input voltage goes beyond the range, in the sense, the ADC may clip the signal or become damaged. And then the last thing is power consumption. So in an ADC, power consumption is an important consideration as it affects the device performance, accuracy and energy efficiency. So the power consumption of an ADC is typically depend on several factors, including the ADC resolution, sampling rate, input voltage range and operating voltage, something like that. Okay, so this is all about ADC. Now let's move to the main thing, which is we are going to talk about the sensor, which is LM35 temperature sensor. So the LM35 is a popular temperature sensor which is used in many electronic projects. It is precision integrated circuit temperature sensor that provides an output voltage proportional to the Celsius temperature. So this sensor has a linear output and its temperature sensitivity is 10 millivolt per degree Celsius. So the sensor can measure temperatures in range of like minus 55 degrees Celsius to plus 150 degrees Celsius with an accuracy of plus or minus 0.5 degrees Celsius. So this sensor is easy to use and require no external calibration or like trimming. It has a low output impedance and can drive long cables without significant, the signal degradation. So the LM35 temperature sensor is widely used in industrial, automotive and medical applications as well as in hobbies projects also. Okay, so now let's directly move to the project setup. Let me open my ID. So before that I want to share you something which is nothing but you can convert this masterclass into 1 month internship on STM32. So the registration amount is just for 1,999, but there is a discount amount which is available for you, which is only for 799. So use this registration link to make your registration. And you will get 30 days of live plus recorded session, 30 days of presentations for download, 5 project source code for download, 1 month internship certificate, participation certificate, 90 days of access to the courses, 4 hackathon live sessions, and you can join to the community group. And also there is a 3-in-1 bundle course is available for you, in which STM32 is a default one, you can't change that. Among these 4 courses you can choose any 2 by your own. So the actual amount of this bundle course is for 3,000 rupees, but there is a discount amount which is available for you, which is only for 1199. So use this registration link to register for 3-in-1 bundle course. So you will get 90 days of live plus recorded session, 90 days of presentation for download, 10 project source code for download, 3 internship certificate, 1 year validity to the courses, hackathon live sessions, and you can join to the community group, and as well as you will get assignments and mock test. And the main thing is, while making your payment, don't forget to add the courses in the domain tab. That's it. Okay, so now let's move to the IDE. Let me go for a new project. Here STM32 F446 RED6. Let me go for a test. So here as usual, go to system core or CC, enable this HSE, and then go for sys. Here I am going to enable the serial wire debugging. Okay, so this is because we are going to use PuTTY software, right? And then you can go to analog ADC1 input 0 channel and make sure that go for parameter settings and make sure that you have resolution as 12 bit, right? And then you have to enable this continuous conversion mode. We have to enable this, right? And then go for connectivity USR2, enable this asynchronous, and then go to clock configuration, change this to HSC, PLL clock, and here I am going for 8 megahertz, and here I am just going to give 16 megahertz. This is pretty much enough for this ADC. Okay, so let me save this. Okay, so here is our defaultly generated code. So here what we need to do is that I am going to add, include STM32F4 series, right? So XS underscore, I am going to use HAL.H library, and then include stdio.h library, the standard input output .h library, right? And then okay, over here I am going to write few lines for printf function. So integer type input output put character, inside I am going to pass like integer type ch. Okay, so inside I am going to give HAL UART transmit, instead I am going to pass HUR2, and then here I am going to pass unsigned integer 8 underscore t with pointer, and then ch, and then I am going to give 1, and then I am going to give HAL max delete. Okay, and then I am going to return that ch, right? And then we can go for main function, scroll down, and over here I am going to add two things. So unsigned integer 32 underscore t ADC value, I am going to initialize this with 0, and then float type. Okay, float type temperature, this is also I am going to initialize this with 0, and then we can go for while loop. So inside I am going to start the conversion using HAL ADC start. So inside address of HADC1, okay, and then I am going to poll the ADC1 peripheral and the timeout to just 1 millisecond. So using HAL ADC poll for conversion. So inside address of HADC1 and then HAL max delete, and then I am going to read the ADC conversion result. So we have already created this variable, right? So ADC value, here I am going to store that. So HAL ADC get value, inside we need to pass address of HADC1. Okay, and then I am going to convert the ADC value to temperature in degree Celsius. For that we have already created one temperature which is equal to ADC value. I am going to multiply this with 3.3 volt. Okay, and then I am going to divide it by 4096.0 and then again 100.0. Okay, so here 3.3 is nothing but a reference voltage. We can't able to give V over here, just 3.3. Okay, so 3.3 is the reference voltage and 4096 is ADC resolution for 12 bit, and 100 is the conversion factor for LM35. I have already told you that 10 millivolt per degree Celsius, right? Now I am going to print the temperature using UR. So using print F, I am going to pass temperature. Okay, so temperature, here I am going to give like percentage of 0.2 F, which is nothing but it will print the thing in float. Okay, and then degree Celsius, right, /n, it will print in the new line, and then temperature. Okay, and then let me end it with a delay of 1 second. That's it. Let me save this. Do we have any bug over here? Printf temperature. Okay, fine. So let me build this. See, we will get an error on this particular line. This is why, because this support for printing floating numbers. So by default, printf in STM32 does not support floating point formatting unless enabled explicit. For that, what we have to do is that go for your project, right click on it, go for properties, and you will able to find the option called C++ build. Go to settings, and over here there is a thing called MCU MPU settings, and you can see 2 options. So you have to enable this, use float with printf and use float with scanf. Just apply and close. Now build it again. Again one error. Let me check. Where it is. They are still having error. Let me check it once. So everything is correct actually. Driver. Source. F publics, and here I need to give HAL. Let me save this and just go for a new project. So go for system core or CC, and then sys, enable this, and go to analog ADC one channel, and just enable this, and then go to connectivity ESR2 asynchronous, and go for here 8, 60, hit enter. Now save this. So over here, let me build this. Here you need to give 32 underscore 2 ADC value which is equal to 0, and then float temperature which is also equal to 0. So let me build it once again. Okay, so now inside this one. Of HADC 1. Okay, so that's it. So after this, temperature which is equal to, I'm going to give like ADC value that has to be multiplied with 3.3 divided by 4096.0, and then the total has to be multiplied by 10. Printf inside temperature percentage .2F. Okay, so Celsius, degree Celsius, or let it be, okay, that's enough. And temperature, so here it should not be like this, right? This hot delay, let me save this and go to here, properties, settings, this one, apply and close. Let me build this. Still we have an error over here, which is ADC pole for conversion. This has to be like this. Okay. Program, everything is right, but there is something issue with the old program. Okay, it's fine. Okay, so now what I'm going to do is that here I have connected my LM35 sensor with STM32 board. So the first pin has to be connected with, here I provide a 5 volt, and the center pin has to be connected with PA0, and the third pin has to be connected with ground of STM32, right? So now I'm going to I'm going to uploading this program into our controller. It's uploading. It's successfully uploaded. Now let me open Putty software, and you have to change. So after installing, so please install Putty software in your PC or laptop, and then go for your software and go for serial. Here you have to change the COM -4, and the speed is not 9600, 1152. This is the baud rate, and just click open. So it will print the temperature like this. Temperature I have 21.99, 21 point something, 22 point something. This is how it will print the output in the Putty software. So you can also view the output in the console page also, or else if you want to show your output like this in the sense, you can go for it also. This is how you will get your output in Putty software. Okay. So again I'm telling you this. So you can convert this masterclass into 1 month internship on STM32. So the actual amount of this 1 month internship is for 1,999, but there is a discount amount which is available for you, which is only for 799. So use this registration to register. And then in this 1 month internship, you will get 30 days of live plus recorded session, 30 days of presentation for download, 5 project source code for download, 1 month internship certificate, participation certificate, 90 days of access to the courses, 4 hackathon live sessions, and you can join to the community group. And also there is a 3-in-1 bundle course is available for you. So in the lineup, you can choose any 2 courses by your own. STM32 is a default one, you can't change that. So the actual amount of this bundle course is for 3,000 rupees, but there is a discount amount which is available for you, which is only for 1199. So use this registration link to register for 3-in-1 bundle course. So in this bundle course, you will get 90 days of live plus recorded session, 90 days of presentations for download, 10 project source code for download, 3 internship certificate, 1 year validity to the courses, hackathon live sessions, and you can join to the community group, and you will get your assignments and mock test. So while making your payment, don't forget to add the courses that you want in the domain tab. So that's all about this session.